The concept of the atomic void is one of the most repeated mistakes in popular science. It is often claimed that atoms are mainly empty space, and that matter is composed chiefly of nothing. This idea is based on the assumption that atoms are composed of tiny nuclei surrounded by much larger electron clouds, and that the distance between the nucleus and the electrons is comparable to the size of the atom itself. However, this picture is misleading and contradicts the principles of quantum theory, which describes the physics of molecules, atoms, and subatomic particles. In this article, we will explain why the empty atom picture is wrong, and how quantum theory provides a more accurate and consistent description of atomic and molecular structure. The wave-particle duality. According to quantum theory, the building blocks of matter, like electrons, nuclei, and the molecules they form, can be portrayed either as waves or particles. This is known as the wave-particle duality, and it implies that these systems have both wave-like and particle-like properties, depending on how we observe them. When we leave them to evolve by themselves without human interference, they act like delocalized waves in the shape of continuous clouds. On the other hand, when we attempt to observe these systems, they appear to be localized particles, something like bullets in the classical realm. The wave-like behavior of matter is described by a mathematical function called the wave function, which encodes all the information about the system. The wave function can be used to calculate the probability of finding a particle in a given region of space at a given time. The probability distribution is proportional to the square of the wave function, and it is often represented by a density plot or a contour map. The regions where the probability is high are called high-density regions, and they indicate where the particle is most likely to be found. The regions where the probability is low or zero are called low-density or zero-density regions, and they indicate where the particle is unlikely or impossible to be found. The particle-like behavior of matter emerges when we perform a measurement on the system. A measurement is any interaction that reveals some information about the system, such as its position, momentum, energy, or spin. When we measure a property of a particle, we obtain a definite value with some uncertainty. However, this value is not predetermined by the wave function, but rather randomly selected from a range of possible values according to the probability distribution. Moreover, the measurement process affects the system in an irreversible way, changing its wave function from its original state to a new state that corresponds to the measured value. This phenomenon is known as the collapse of the wave function or quantum decoherence. The fallacy of the empty atom. The empty atom picture is based on two fallacies, one about the size of atomic nuclei, and one about the nature of electron clouds. The first fallacy is that atomic nuclei are tiny dots compared to the size of atoms. This is true only if we consider nuclei as particles with well-defined positions and sizes. However, as we have seen, nuclei are also waves that can spread over large regions of space. From a quantum perspective and for conceptual consistency, nuclei should be depicted on the same footing as electrons, as clouds as well. Moreover, nuclei are not static objects, but rather dynamic systems that can undergo various processes such as nuclear fission, fusion, decay, or rotation. These processes can affect their shape and size, making them even more diffuse and complex. The second fallacy is that electron clouds are empty spaces where nothing happens. This is false for several reasons. First, electron clouds are not empty spaces, but rather regions where electrons have a high probability of being found. Second, electron clouds are not static shapes, but rather dynamic patterns that change over time according to quantum laws. Third, electron clouds are not isolated entities, but rather interacting systems that can exchange energy and information with other particles or fields. For example, electron clouds can be affected by electric or magnetic fields, by photons or other particles of light, or by other electron clouds in neighboring atoms or molecules. The fullness of matter. A more accurate picture of atoms and molecules is one that recognizes their fullness rather than their emptiness. Matter is composed not chiefly of nothing, but rather of something, quantum fields. Quantum fields are mathematical objects that describe how particles behave and interact in space and time. Quantum fields can be seen as collections of waves or vibrations that fill all space and create particles when they are excited or disturbed. Quantum fields can explain both the wave-like and particle-like behavior of matter. When quantum fields are in their lowest energy state, called the vacuum state, they do not produce any particles and appear as empty space. However, when quantum fields are excited by some external source, such as a measurement device, they can create particles that appear as localized lumps of energy and matter. These particles are not separate from the fields, but rather manifestations of them. Moreover, quantum fields can also explain the interactions between particles, such as the electromagnetic force or the nuclear force. These interactions are mediated by other particles, called force carriers or bosons, that are also created by quantum fields. Quantum fields provide a more complete and consistent picture of atomic and molecular structure than the empty atom picture. Quantum fields show that atoms and molecules are not mainly empty space, but rather filled with waves and particles that are constantly changing and interacting. Quantum fields also show that atoms and molecules are not isolated systems, but rather connected with each other and with the rest of the universe through quantum entanglement. Quantum entanglement is a phenomenon where two or more particles share a quantum state and remain correlated even when they are separated by large distances. Quantum entanglement implies that the properties of one particle can affect the properties of another particle instantaneously, regardless of the space or time between them. The empty atom picture is a misconception that misunderstands quantum theory and misrepresents atomic and molecular structure. The empty atom picture assumes that atoms are composed of tiny nuclei surrounded by much larger electron clouds, and that there are large empty spaces within the atom. However, quantum theory shows that both nuclei and electrons are waves and particles that can spread over large regions of space, and that there are no empty spaces within the atom. Quantum theory also shows that atoms and molecules are not static shapes, but rather dynamic patterns that change over time and interact with other systems. Quantum theory further shows that atoms and molecules are not composed chiefly of nothing, but rather of something, quantum fields. Quantum fields are collections of waves and particles that fill all space and create matter and energy. Quantum fields also explain the interactions between particles and the connections between systems through quantum entanglement. The empty atom picture is likely the most repeated mistake in popular science, but it is also one of the most fascinating topics to explore. By learning more about quantum theory and quantum fields, we can gain a deeper understanding of the nature of matter and reality, and appreciate the beauty and complexity of the atomic and molecular world.